Far below the surface of the ocean, beneath the waves and beyond the reach of sunlight, there is a hidden layer of water where sound behaves in a way that almost seems unnatural. In this narrow zone, sound does not fade quickly into silence. It bends, folds, and carries itself through the dark for thousands of miles, guided by invisible gradients of temperature and pressure deep within the sea. A whale call made in one part of the ocean can travel across an entire basin. An earthquake beneath the seafloor can announce itself to instruments hours away. For decades, submarines moved through this same corridor while unseen hydrophones listened in silence. This hidden pathway is known as the SOFAR Channel, one of the most extraordinary acoustic features on Earth. Tonight, we'll explore how the SOFAR Channel was discovered, how it transformed submarine warfare during the Cold War, how whales have used it for millions of years, and how it revealed some of the strangest sounds ever recorded in the ocean's depths. SOFAR is an acronym. It stands for Sound Fixing and Ranging Channel. Each word in the name describes a specific function: sound, because the channel is defined by the way acoustic energy moves through seawater; fixing, because the original purpose humans had in mind for it was fixing the position of something lost at sea, using the channel to locate a person, a pilot, a signal far from any shore; ranging, because the channel reaches across ocean basins, extending from one coastline toward another at a scale that makes most human conceptions of distance feel inadequate. The word channel implies a pathway, a route that something moves through with regularity. In this case, what moves is sound. Low-frequency acoustic energy, produced by whales and earthquakes and underwater explosions and the machinery of ships, enters this corridor at depth and travels through it with an efficiency that no other part of the ocean can match. The name SOFAR was given to the channel by the scientists who discovered it, and it has remained in use ever since, a compact label for one of the more consequential acoustic features of the natural world. The SOFAR Channel is not unique to any single ocean. It runs continuously beneath the surface of the Atlantic, the Pacific, the Indian, the Arctic, and the Southern Ocean, threading through each basin as an unbroken zone of acoustic efficiency. It leaves no visible mark on the surface. No instrument lowered from a ship will touch a wall or a boundary. The channel has no physical structure. It is defined entirely by the physics of pressure and temperature, by the way those two forces interact to produce a layer of water where sound speed reaches a minimum. Because that minimum exists wherever the ocean is deep enough and old enough in its thermal structure, the channel is a planetary feature. It is present in cold water and warm water, in the tropics and near the poles, in water that is thousands of meters deep and in water that is only a few hundred meters deep. It follows the contours of the Earth's ocean basins, adjusting its depth to the local conditions of temperature and pressure, but never disappearing. Oceanographers describe it as a waveguide, a natural structure that traps sound within a limited zone and allows it to travel far greater distances than it could in open, unstructured water. The SOFAR Channel was identified in 1944 by American oceanographer Maurice Ewing and his colleague J. Lamar Worzel, working under a contract with the United States Navy. Ewing was a geophysicist with broad interests in how waves moved through the Earth's crust and oceans. Worzel was his research partner and collaborator. The two were studying the acoustic properties of the deep ocean at a time when the Navy had a direct military interest in understanding how sound traveled through seawater. Ewing and Worzel conducted experiments in the Atlantic, introducing sounds at measured depths and recording how far those sounds could be detected by receivers positioned at various distances. Their results confirmed a theoretical prediction. At a specific depth, sound traveled far greater distances than at any other depth in the water column. That depth corresponded to the layer of minimum sound speed, which Ewing recognized as a natural acoustic waveguide. Their findings were classified for several years, but the scientific significance of the discovery was clear from the beginning. The SOFAR Channel became the foundation for military underwater surveillance systems, long-range rescue technology, ocean monitoring programs, and an entirely new understanding of how marine animals communicate across distances that, prior to 1944, no one had considered acoustically feasible. In most of the world's oceans, the SOFAR Channel is centered at a depth of roughly 600 to 1,200 meters. 600 meters is approximately twice the height of the Eiffel Tower measured below the sea surface. At that depth, sunlight is absent. The water temperature is near freezing. The pressure is roughly 60 atmospheres, 60 times the pressure at the ocean's surface. This is the zone where the channel's core acoustic properties develop, where temperature has cooled enough to slow sound significantly, and where pressure has not yet risen enough to compensate fully and speed it back up. The result is a layer of minimum sound speed that functions as the channel's acoustic axis. Sounds introduced at or near this depth from above or below are gradually refracted, bent, back towards the axis rather than escaping into the surrounding ocean. The depth of 600 to 1,200 meters is not a fixed boundary. It shifts with latitude, season, and local oceanographic conditions. But within this range, across the world's major ocean basins, the channel maintains its character, a zone of slow sound speed, efficient propagation, and remarkable acoustic reach. Near the equator, the SOFAR Channel sits deeper than it does elsewhere in the world's oceans, sometimes reaching 1,200 meters below the surface. The reason is thermal. The tropical sun warms the upper ocean to greater depths than at higher latitudes, creating a thick layer of warm water above the channel. Because warm water speeds sound up, the minimum sound speed layer, the core of the SOFAR Channel, is pushed downward, below the warm surface layer, to depths where the cooling effect of temperature begins to dominate. The channel follows the thermal structure of the ocean wherever it goes, and in the tropics, that structure pushes it deep. A ship crossing the equatorial Pacific or Atlantic passes over a SOFAR Channel that lies farther below it than in almost any other part of the ocean. The sound traveling through that channel is separated from the surface world by more than a kilometer of water. Warm above, cold at the channel's core, dense and dark throughout. At high latitudes, near the Arctic and Antarctic, the SOFAR Channel rises close to the surface. In some regions, to within a few hundred meters of the sea. The reason is the opposite of what drives it deep in the tropics. Polar seawater is cold from the surface downward, with very little thermal gradient between the upper layers and the deep. Without a thick, warm surface layer to suppress the minimum speed zone, the channel axis moves upward. In some polar regions, it effectively merges with the upper water column, meaning that sounds near the surface can couple into the channel with unusual ease. This has implications for the animals living in those waters. Bowhead whales in the Arctic, for example, produce calls that may interact with the shallow SOFAR Channel in ways that are still being studied. The channel, in this sense, is not a static structure. It breathes with the thermal state of the ocean, rising in cold regions and sinking in warm ones, adjusting continuously to the conditions around it. Sound travels through air at sea level at approximately 343 meters per second. In seawater, it travels at approximately 1,500 meters per second, roughly 4.4 times faster. The difference comes down to the physical properties of the medium. Water is denser than air, and its molecules are more tightly packed. When pressure waves pass through it, energy is transferred between molecules more efficiently, and sound propagates faster as a result. This speed advantage is one reason the ocean functions as such an effective acoustic environment. A sound produced in the SOFAR Channel reaches a receiver 1,000 kilometers away in approximately 11 minutes. The same distance in air would take roughly 48 minutes under ideal conditions. In practice, sound in air attenuates so quickly over large distances that the comparison becomes theoretical rather than practical. In the SOFAR Channel, 1,000 kilometers is a routine distance for low-frequency acoustic signals to travel with measurable coherence. The contrast between 343 meters per second, the speed of sound in air at sea level, and approximately 1,500 meters per second, the speed of sound in seawater, is one of the more useful numbers in acoustic oceanography. At 1,500 meters per second, a sound pulse in the SOFAR Channel covers 90 kilometers in 1 minute. In 1 hour, it covers 5,400 kilometers. That figure, 5,400 kilometers per hour, is roughly equivalent to the cruising speed of a supersonic aircraft. Acoustic signals from underwater earthquakes, whale vocalizations, and deliberately introduced research pulses routinely travel at this speed through the channel, crossing ocean basins in hours and arriving at distant receiver arrays with enough signal strength to be detected and analyzed. The speed of sound in water is not an abstract number. It is the rate at which the ocean's acoustic record is written across its own geography. the speed at which events in one part of the ocean announce themselves to instruments thousands of kilometers away. Sound does not travel in a straight line through the ocean, it bends. When a sound wave moves from a region where it travels faster into a region where it travels more slowly, it curves toward the slower region. This bending is called refraction, and it is governed by Snell's law, a principle described by Dutch mathematician Willebrord Snell in 1621, derived from observations of how light behaves at the boundaries between materials. In the ocean, refraction operates continuously and three-dimensionally. Sound moving downward from the warm, fast surface layer into the cooler, slower water below bends toward the SOFAR Channel axis. Sound moving upward from the high-pressure depths, where speed increases with pressure, also bends toward the axis. Both groups of sounds are directed by refraction into the same corridor. The channel does not need walls to trap sound. The gradients of temperature and pressure above and below it do that work continuously, bending sound back toward the axis before it can escape into the surrounding ocean. Engineers who design fiber optic cables and microwave waveguides use a principle that the ocean arrived at through physics alone. Confine a wave within a limited space, and it will travel far greater distances with far less energy loss than it would in an open, unstructured medium. The SOFAR channel is a natural waveguide of this kind. Without it, a sound produced at depth in the open ocean would spread outward in all directions, upward, downward, laterally, and its energy would diminish with the square of the distance traveled, becoming inaudible within a relatively short range. Within the SOFAR channel, that spreading is constrained. Refraction curves sound back toward the channel axis before it reaches the seafloor or the surface, preventing the energy losses that occur when sound bounces off those boundaries. The result is a propagation environment in which low-frequency sound can travel thousands of kilometers while retaining enough energy to be detected by sensitive instruments. The SOFAR channel achieves this not through any structural complexity, but through the straightforward application of two physical gradients, operating in opposite directions, converging on a single axis. A low-frequency acoustic signal introduced into the SOFAR channel at the appropriate depth can travel thousands of kilometers while remaining coherent, meaning that it retains enough of its original frequency structure and timing to be identified, measured, and analyzed at the receiving end. In the early SOFAR experiments of 1944, small explosive charges detonated at SOFAR depth in the Atlantic Ocean were detected clearly by hydrophone receivers more than 2,000 miles away. Later experiments and monitoring data extended that range further. Whale calls produced in one part of an ocean basin have been detected by receivers on the opposite side. Earthquake signals have crossed entire ocean basins and arrived at hydrophone arrays with enough signal strength to allow precise location estimates. The channel's ability to preserve acoustic coherence over these distances is the property that makes it useful for communication, surveillance, scientific monitoring, and, in the biological case, long-range animal coordination. It is not that the channel amplifies sound. It simply prevents the losses that would otherwise reduce sound to inaudibility long before it could cross a significant fraction of an ocean basin. The SOFAR channel has no physical boundaries. There are no walls, no floor, no ceiling, nothing that could be touched, measured with a depth gauge, or observed through a camera. It is a zone defined entirely by gradients in the physical properties of water. The upper boundary of the channel is not a surface, but a region where water temperature begins to increase enough to speed sound above its minimum value. The lower boundary is a region where pressure becomes high enough to do the same. Between those two gradients, sound speed is at its minimum, and refraction keeps sound confined to that zone. This absence of physical structure is one of the more conceptually demanding things about the SOFAR channel. It is real. It has measurable effects on acoustic propagation, and those effects have been documented in thousands of experiments and observations over 8 decades. But it exists only as a consequence of physics, a feature of the ocean that has no substance apart from the mathematics that describes it. Understanding the SOFAR channel requires accepting that some of the most significant structures in the natural world are made not of matter, but of gradients. The speed of sound in seawater is controlled by 3 physical variables: temperature, salinity, and pressure. Temperature is the dominant factor in the upper ocean, where differences of 10 degrees Celsius or more between the warm surface layer and the cooler water below produce significant changes in sound speed. Salinity plays a secondary role, Saltier water is slightly denser and transmits sound marginally faster than fresher water of the same temperature and pressure. Pressure becomes the dominant factor in the deep ocean, where temperatures are uniformly cold and differences in salinity are small. These three variables interact across every depth in the water column, creating a sound speed profile that is unique to each location and season. Oceanographers measure this profile by lowering instruments called CTDs, conductivity, temperature, and depth sensors, through the water column. The resulting data produces a vertical map of sound speed that shows, in most ocean locations, a distinct minimum at some intermediate depth. That minimum is the SOFAR Channel axis, the point at which all three variables combine to produce the slowest possible sound propagation. Among the three variables that control sound speed in seawater, temperature has the strongest effect in the upper ocean. Warmer water transmits sound faster because heat increases the kinetic energy of water molecules, allowing pressure waves to propagate more efficiently between them. For every degree Celsius increase in water temperature, sound speed increases by roughly 4 to 5 meters per second. In the tropical ocean, where surface temperatures can reach 28 or 30 degrees Celsius and the warm layer extends to several hundred meters depth, sound near the surface travels significantly faster than it does in the cold, deep water below. This thermal stratification is the primary force that shapes the upper boundary of the SOFAR Channel. As sound descends from the warm surface layer into cooler water, it slows, bending downward toward the channel axis. The thermal gradient of the ocean, warm above, cold below, acts as the upper lens of the channel's trapping mechanism, redirecting sound that would otherwise escape upward back toward the zone of minimum speed. Pressure increases with depth at a rate of approximately 1 atmosphere for every 10 meters of water. At 600 meters, the shallow limit of the SOFAR Channel in many ocean regions, the pressure is roughly 60 atmospheres. At 1,200 meters, it is approximately 120 atmospheres. This pressure compresses seawater slightly, bringing its molecules into closer proximity and increasing the efficiency with which they transmit acoustic energy. The effect on sound speed is measurable and consistent. Sound travels approximately 1.7 meters per second faster for every 100 meters of additional depth due to pressure alone. This pressure-driven increase in sound speed forms the lower boundary of the SOFAR Channel. Below the channel axis, as depth and pressure continue to increase, sound begins to speed up again, even though the water remains cold. Sounds that descend below the axis are moving into faster water and refract back upward toward the minimum speed zone. The pressure gradient below the channel does the same work that the temperature gradient does above it. It turns sound around before it can escape. The SOFAR Channel exists because temperature and pressure affect sound speed in opposite ways, and at a specific depth, their combined effect reaches a minimum. Above the channel axis, temperature decreases with depth, which slows sound down. Below the axis, pressure increases with depth, which speeds sound back up. The two forces oppose each other across the full vertical extent of the water column. In the upper ocean, the temperature effect dominates and sound slows as depth increases. In the deep ocean, the pressure effect dominates and sound speeds up as depth increases. The crossover point, where neither force dominates completely and sound speed reaches its lowest value, is the SOFAR Channel axis. Its exact depth depends on the local temperature and salinity profile. In warm ocean regions where the temperature gradient is steep, the crossover occurs deeper. In cold polar waters, where temperature is uniform from surface to bottom, the crossover may occur very near the surface. But the underlying physical logic is the same wherever the channel exists. Two gradients, pulling in opposite directions, meeting at a single depth. At the core of the SOFAR Channel, the depth where temperature and pressure effects combine to produce the slowest sound propagation, sound travels at approximately 1,450 to 1,480 meters per second in typical open ocean conditions. This is the minimum sound speed layer, sometimes called the channel axis. It is the acoustic center around which the entire waveguide structure organizes itself. Sound above the axis is in slightly warmer, faster water. Sound below the axis is under greater pressure, also faster. Both are in a region of higher sound speed relative to the axis, and both are therefore refracted, bent, toward the axis by Snell's law. The minimum sound speed layer is not a sharp boundary. It is a gradual transition zone, a few hundred meters thick in most ocean locations, within which sound speed is near its minimum value. But the axis itself, the depth of absolute minimum speed, is precise enough to be identified from oceanographic measurements, and it is the depth at which acoustic propagation is most efficient, where the channel's trapping effect is strongest and the potential range of signal transmission is greatest. Snell's law describes the relationship between the angle at which a wave travels and the speed of that wave in the medium it occupies. When a wave moves from a region of higher speed into a region of lower speed, it bends toward the boundary between the two regions. When it moves from slower to faster, it bends away. In the ocean, this means that sound is continuously deflected toward the SOFAR Channel axis from both above and below. Sound descending from the warm surface layer enters progressively cooler, slower water and bends downward toward the minimum speed zone. Sound rising from the high-pressure depths enters progressively lower pressure, slower water and bends upward toward the same zone. Snell's law is not a special property of the ocean. It applies to all waves in all media. It governs the refraction of light through glass, the bending of seismic waves through the Earth's interior, and the focusing of radio waves in atmospheric waveguides. In the ocean, it operates on sound continuously and three-dimensionally, creating the SOFAR channel not through any unique oceanic property but through the universal physics of wave propagation in a medium with a gradient in wave speed. Sound in shallow water loses energy rapidly because it bounces repeatedly between the ocean surface and the seafloor. Each reflection at the surface scatters some energy into the atmosphere. Each reflection at the seafloor transfers some energy into the sediment and rock below. Over a series of reflections, the sound's amplitude diminishes and its coherence degrades. In the SOFAR channel, this mechanism does not operate. Sound traveling through the channel is refracted back toward the axis before it reaches either boundary, so it never strikes the seafloor or the surface. It does not reflect. The only energy losses are absorption, the conversion of a small fraction of acoustic energy into heat as it passes through seawater, and geometric spreading, the natural decrease in intensity as a sound wave expands outward from its source. Both losses are far smaller than the reflection losses in shallow water. Absorption in seawater at low frequencies is extremely small over distances of hundreds to thousands of kilometers. Geometric spreading in the SOFAR channel is cylindrical rather than spherical. The sound spreads in 2 dimensions rather than 3 because vertical spreading is constrained by the channel, which means energy density decreases more slowly with distance than it would in open, unbounded water. The seafloor and the ocean surface are both imperfect reflectors that reduce acoustic energy with every interaction. The seafloor is composed of sediment and rock with acoustic properties that absorb a significant portion of incident sound energy and scatter the remainder in unpredictable directions. The ocean surface is in constant motion, broken by waves and surface roughness that scatter incoming sound and introduce variability into the reflected signal. A sound that travels by repeated reflection between these 2 boundaries, as sound does in shallow coastal waters, loses a portion of its energy at each bounce. Over the distances relevant to long-range ocean acoustics, these losses accumulate until the original signal is undetectable. The SOFAR channel's primary advantage is that it eliminates this loss mechanism entirely. Sound in the channel does not reach either boundary. It curves before it gets there, returning toward the axis, traveling forward through the water column without ever contacting the surfaces that would degrade it. The channel essentially removes the 2 biggest obstacles to long-distance underwater sound propagation by keeping sound away from them. Acoustic coherence refers to the degree to which a sound signal retains its original structure, its frequency content, its timing, its recognizable character, as it travels from source to receiver. A signal that arrives coherent is one that can be analyzed. Its frequency can be measured, its travel time can be determined, its origin can in some cases be identified. A signal that has lost coherence arrives as noise, detectable perhaps, but not interpretable. The SOFAR channel preserves coherence over distances that would destroy it in any other acoustic environment. Low-frequency signals, whale calls, earthquake signals, research pulses, have been detected and analyzed after traveling across entire ocean basins, retaining enough of their original structure to allow precise measurement of arrival time, source frequency, and in some cases, source location. This coherence is not incidental. It is the direct result of the channel's waveguide properties. By preventing reflection losses and constraining geometric spreading, the channel allows signals to arrive at distant receivers with enough amplitude and structural integrity to be scientifically useful. The SOFAR channel allows a single acoustic event, a pulse of sound produced at depth, to travel across an entire ocean basin and arrive at a receiver on the far side with measurable coherence. This is not a theoretical projection. It has been demonstrated experimentally and observed in natural data. Acoustic pulses introduced at SOFAR depth in the Indian Ocean have been detected at receivers in the Pacific. Whale calls produced in the North Atlantic have been recorded by hydrophones in the South Atlantic. Earthquake signals from the mid-ocean ridges have been detected by arrays on opposite sides of the same basin within minutes of their occurrence. The time it takes for a signal to cross an ocean basin at SOFAR propagation speeds is a matter of hours. A signal produced off the coast of one continent arrives at the far shore roughly 2 to 3 hours later, depending on distance and the exact sound speed structure it passes through. For the duration of that journey, the signal is a physical reality, a pattern of pressure variations moving through cold water at 1,500 meters per second, carrying information about the event that produced it to any instrument positioned to receive it. Maurice Ewing was a geophysicist at Columbia University when the United States Navy recruited him to study underwater sound propagation during the Second World War. Ewing had a background in seismic research, the study of how elastic waves travel through the Earth, and the Navy's question was a natural extension of that expertise into the ocean environment. Submarines had become a significant factor in naval warfare, and understanding how sound traveled through seawater was operationally important. The Navy needed to know, how far does sound travel underwater, at what depths does it travel most efficiently, and what determines its range? Ewing took on the problem with characteristic methodical rigor, conducting measurements in the Atlantic and developing a theoretical framework for understanding acoustic propagation in the deep ocean. His collaborator in this work was J. Lamar Worzel, a careful and systematic researcher who helped design and execute the experiments that confirmed their theoretical predictions. Together, Ewing and Worzel identified the minimum sound speed layer and recognized its properties as a natural acoustic waveguide, the feature that would become known as the SOFAR Channel. The military context that drove the discovery of the SOFAR Channel was the submarine warfare of the Second World War. German U-boats were inflicting significant losses on Allied shipping in the Atlantic, and the Allies were investing heavily in submarine detection technology. Acoustic methods, using the sounds submarines produced to locate them, was central to that effort. The Navy needed a thorough understanding of how sound propagated through the ocean at different depths, under different temperature and salinity conditions, at different frequencies. This need produced a generation of acoustic oceanographers who combined physical theory with direct observation in ways that had not been attempted before. The knowledge they developed about underwater sound propagation, including the discovery of the SOFAR Channel, was a byproduct of that military research effort. The science and the operational requirement reinforced each other throughout the war years and into the Cold War period that followed. The need to understand submarine acoustics produced an understanding of ocean acoustics generally, an understanding that would eventually be applied to earthquake monitoring, climate science, and the study of marine mammals. In 1944, Maurice Ewing and J. Lamar Worzel conducted a series of acoustic experiments in the Atlantic Ocean to test the theoretical prediction that sound introduced at the depth of minimum sound speed would propagate over unusually long distances. The experimental method was direct. Small explosive charges were detonated at controlled depths, and the resulting acoustic signals were recorded by hydrophone receivers positioned at various distances from the detonation point. Charges detonated at SOFAR depth produced signals detected at distances of several hundred miles, with clarity that demonstrated the channel's waveguide properties. Charges at other depths produced signals with significantly shorter detection ranges. The results confirmed the theoretical model. The minimum sound speed layer was acting as a waveguide, trapping sound within a limited depth range and allowing it to travel far beyond the distances achievable through normal spherical spreading. The experiments were conducted under wartime conditions, with the findings classified by the Navy. Their significance was clear, however, and the knowledge they produced became the foundation for several subsequent military and civilian programs. The most immediately striking result from the 1944 SOFAR experiments was the detection of small explosive charges by hydrophone receivers at distances of several hundred miles. In air, a small explosive charge of the type used in the experiments would be audible over a few miles at most. In shallow coastal water, its signal would attenuate quickly through reflection losses. But at SOFAR depth in the Atlantic, the same charges produced signals that traveled hundreds of miles with enough amplitude to be clearly detected and recorded. The detection ranges achieved in these experiments were far beyond what acoustic scientists had previously documented in water. They represented a practical demonstration of the SOFAR Channel's efficiency as a propagation medium, not just a theoretical property of the ocean's sound speed profile, but a measurable reality with direct operational implications. The Navy took those implications seriously, and the experiments of 1944 led directly to the development of the first practical applications of SOFAR technology, a rescue positioning system for personnel lost at sea. The first practical application proposed for the SOFAR Channel was a rescue positioning system for military personnel lost at sea. Developed in 1944 and 1945, the system was designated Project SOFAR. The concept was straightforward. Equip pilots, sailors, and other personnel who might be forced into the ocean with a small explosive charge and the means to deploy it at SOFAR depth. If a person was lost at sea, they would release the charge. It would sink to the appropriate depth and detonate, sending an acoustic signal into the SOFAR Channel. Shore-based hydrophone stations monitoring the channel continuously would detect the signal. Because multiple stations would detect the signal at slightly different times, the position of the detonation could be calculated by triangulation. And that position would correspond to the location of the survivor. The system was designed to work over ranges of hundreds to thousands of miles, covering ocean areas that conventional search and rescue methods could not reach effectively. It was one of the first practical uses of long-range underwater acoustics, and it demonstrated the potential of the SOFAR Channel as a medium for position reporting over oceanic distances. The Project SOFAR rescue system was designed to be operable by a survivor under field conditions, someone who might be in cold water, in a life raft, possibly injured, with minimal equipment and limited time to take action. The explosive charge was small, housed in a waterproof casing, and equipped with a pressure-sensitive fuse calibrated to trigger at approximately the depth of the SOFAR Channel in the relevant ocean region. A survivor would release the charge over the side of the raft. As it sank, the fuse would respond to increasing water pressure and trigger the explosive at the target depth. The resulting acoustic signal would enter the SOFAR Channel and propagate outward at 1,500 meters per second. Shore-based receiving stations would record the time of arrival of the signal. Because the signals from a single detonation arrived at different stations at slightly different times, reflecting the different distances between the detonation point and each station, analysts could use those time differences to calculate the geographic position of the explosion. The method, known as time difference of arrival positioning, is conceptually the same principle used by GPS systems today. In the context of 1944, it was a novel and sophisticated application of acoustic physics to a practical problem. A hydrophone is an underwater acoustic receiver, an instrument that detects pressure variations in water and converts them into electrical signals that can be recorded and analyzed. Hydrophones are the oceanic equivalent of microphones, but they are engineered for the specific conditions of the underwater acoustic environment: high ambient pressure, exposure to seawater, sensitivity to frequency ranges that extend below the lower limit of human hearing, and operation over extended periods without maintenance. The hydrophones used in the SOFAR experiments of 1944 were relatively simple by modern standards, but they were sensitive enough to detect the low-frequency signals produced by small explosive charges at ranges of several hundred miles. Later generations of hydrophones developed for the SOSUS network and subsequent oceanographic programs were far more sensitive, capable of detecting signals at the level of individual whale calls across entire ocean basins. Modern hydrophone arrays used in seismic monitoring, ocean acoustic tomography, and biological surveys are among the most sensitive acoustic instruments ever built, able to resolve signals at energy levels that are functionally indistinguishable from the ambient thermal noise of the water itself. Project SOFAR required shore-based receiving stations equipped with hydrophones, recording equipment, and the infrastructure to transmit data to a central analysis facility. Stations were established at multiple points along the United States East Coast and in the Pacific, positioned to provide overlapping coverage of the ocean regions most likely to be relevant in a wartime context. The placement of each station was determined by a combination of acoustic geometry, where it would need to be to provide useful bearing lines on signals in the target ocean area, and logistical factors such as availability of suitable coastal sites, proximity to communication infrastructure, and existing Navy facilities. These stations were the first nodes of what would eventually become a global ocean acoustic monitoring network. Their design established the basic architecture that all subsequent systems followed. Hydrophones at depth in the water column connected by cable to a shore facility with continuous recording and analysis capability. The Project SOFAR shore stations were modest facilities by the standards of the systems that followed them, but they demonstrated the operational viability of the concept and produced the first large dataset of long-range underwater acoustic detections. In testing conducted as part of Project SOFAR, explosive charges detonated at SOFAR depth in the Atlantic Ocean were detected by shore-based hydrophone stations at distances exceeding 2,000 miles. This detection range was substantially greater than anything previously demonstrated for underwater acoustic signals. 2,000 miles is the approximate distance from the eastern United States to the Azores or from the United Kingdom to Iceland and back. At the propagation speed of sound in the SOFAR channel, a signal originating 2,000 miles from the receiving station would arrive approximately 2.4 hours after detonation. The fact that such a signal arrived with enough amplitude to be clearly detected and recorded by 1944-era hydrophones was a direct demonstration of the channel's waveguide efficiency. The detection range also established the practical scale of what a SOFAR-based rescue or surveillance system could cover. A network of shore stations with separations of several hundred miles, each capable of detecting signals from 2,000 miles away, could theoretically cover the entire Atlantic Ocean with overlapping acoustic coverage, a capability that had significant implications for both rescue operations and military surveillance. Project SOFAR was not operationally deployed before the end of the Second World War. The system had been demonstrated successfully in testing, the acoustic physics worked, the detection ranges were confirmed, the positioning calculations were feasible, but the logistics of equipping Allied forces with SOFAR charges, establishing a sufficient number of shore receiving stations, and training personnel in the system's use had not been completed by the time Japan surrendered in August 1945. The war ended before the infrastructure could be put in place. The rescue system that Ewing and Worzel had designed was never used for its intended purpose on an operational scale. The knowledge it was built on, however, survived the end of the war intact. The confirmed detection ranges, the demonstrated feasibility of acoustic positioning over oceanic distances, and the understanding of SOFAR channel propagation that the project had produced all informed the subsequent development of underwater acoustic surveillance systems during the Cold War. Project SOFAR did not save the lives it was designed to save, but the science behind it became the foundation for programs that shaped strategic relations between major powers for 4 decades. The knowledge developed during Project SOFAR confirmed detection ranges of over 2,000 miles, demonstrated feasibility of acoustic positioning, a validated theoretical model of SOFAR channel propagation, was applied almost immediately to the emerging strategic problem of the Cold War. As the Soviet Union developed a submarine fleet capable of threatening US coastal cities and naval assets, the United States Navy recognized that the SOFAR channel could serve as the medium for a global submarine surveillance network. If small explosive charges at SOFAR depth were detectable at 2,000 miles, then a submarine's engine noise and propeller cavitation, produced continuously as the vessel moved through the ocean, might be detectable at comparable ranges, given sufficiently sensitive receivers and sophisticated signal processing. The conceptual step from Project SOFAR to what became SOSUS, the sound surveillance system, was not large. The physics was the same. The channel was the same. Only the acoustic source had changed, from a deliberate explosive to the involuntary mechanical noise of a submarine. The Navy began planning SOSUS in the late 1940s, and construction of the first arrays began in the early 1950s. The sound surveillance system, known as SOSUS, was constructed beginning in the early 1950s as a fixed underwater acoustic surveillance network designed to detect and track Soviet submarines in the Atlantic and Pacific Oceans. The system consisted of hydrophone arrays positioned at or near the SOFAR channel axis, connected by cable to shore-based listening stations where analysts could monitor the incoming acoustic data in real time. The hydrophone arrays were engineered to be sensitive to the low-frequency sounds produced by submarine machinery, engine vibration, propeller noise, and the various mechanical resonances of a vessel operating underwater. These sounds, at the relevant frequencies, entered the SOFAR channel and propagated over long distances, allowing them to be detected by arrays positioned hundreds or even thousands of miles from the submarine's location. SOSUS represented a direct application of the SOFAR science that Ewing and Worzel had developed, scaled up to the geographic requirements of Cold War naval surveillance. It was designed to give the United States Navy awareness of Soviet submarine movements across ocean basins, a capability that, if it worked as planned, would constitute a significant strategic advantage. SOSUS was among the most tightly held secrets in the United States government throughout the Cold War. Its existence was unknown to the public, to most of the scientific community, and to the majority of people working in national security. The level of secrecy was commensurate with the system's effectiveness. SOSUS worked reliably and at the scale intended, and disclosing its existence would have provided the Soviet Navy with the knowledge that its submarines were being tracked, prompting immediate countermeasures. Thousands of military personnel and contractors worked within the SOSUS program over its 4-decade operational life, staffing shore stations, analyzing acoustic data, maintaining the arrays, and producing intelligence reports that reached senior levels of government. None of them spoke publicly about what they were doing. The system's classified status was maintained through compartmentalization, security oaths, and the straightforward recognition that the program's value depended on the adversary's ignorance of it. SOSUS gave the United States Navy a degree of oceanic awareness that fundamentally shaped naval strategy during the Cold War. That awareness would have been degraded or destroyed if the Soviet Navy had known the full extent of what the Americans could hear. Construction of the SOSUS network began in the early 1950s and continued through the 1970s, expanding in geographic coverage and technical sophistication as the Cold War progressed and the Soviet submarine fleet grew in size and capability. The first arrays were installed in the North Atlantic, covering the routes that Soviet submarines would need to cross to reach operational patrol areas. As the Pacific became an increasingly important theater, additional arrays were installed there as well. The engineering challenges of the program were substantial. Arrays had to be positioned at SOFAR Channel depths, sometimes exceeding 1,000 meters, in locations chosen for their acoustic coverage rather than their accessibility. Cables connecting the arrays to shore stations ran for hundreds of miles across the seafloor. The equipment had to function reliably in cold, pressurized seawater without maintenance for extended periods. Solutions to these problems were developed incrementally over 2 decades of construction and operation, producing a network that, by its peak in the 1970s and 1980s, provided broad acoustic coverage of the major submarine transit routes in both ocean basins. The physical infrastructure of SOSUS consisted of 3 main components: hydrophone arrays, undersea cables, and shore receiving stations. The hydrophone arrays were assemblies of multiple acoustic sensors distributed over a baseline of hundreds of meters, which allowed the direction of an incoming sound to be determined from the differences in arrival time at different sensors within the array. The undersea cables connecting the arrays to shore were engineering projects in their own right, laid across miles of seafloor in water depths that precluded conventional repair operations. The shore stations were facilities staffed continuously by trained analysts who monitored the acoustic data streaming in from the ocean floor, searched for submarine contacts, and produced reports on detected tracks. The stations were linked to centralized analysis centers where data from multiple arrays could be combined to produce position estimates and track assessments. The system as a whole was a distributed acoustic network, geographically dispersed but operationally integrated, using the SOFAR channel as the medium through which all its components communicated with each other in the acoustic sense. A submarine detected by an array 1,000 miles offshore sent its acoustic signature through the SOFAR channel to the cable termination, through the cable to the shore station, and from there to the analysts whose job was to interpret it. At operational peak, SOSUS provided the United States Navy with the ability to detect and track Soviet submarines across the Atlantic and Pacific Oceans, from their home bases on the Kola Peninsula and the Soviet Pacific coast, through their transit routes to patrol areas. The capability was not absolute. Submarines that operated very quietly, used favorable ocean floor topography to mask their signatures, or operated at depths and in ocean conditions that reduced their acoustic output could in some cases evade detection. But for much of the Cold War, SOSUS provided a level of oceanic awareness that gave American naval commanders detailed knowledge of Soviet submarine movements at the basin scale. Decisions about the positioning of anti-submarine warfare assets, the routing of convoys, and the deployment of ballistic missile submarines were made with reference to SOSUS intelligence. Crisis situations, including the Cuban Missile Crisis of 1962, were managed with awareness of submarine positions that SOSUS had identified. The strategic value of this awareness was enormous, and the investment the United States made in building and maintaining SOSUS reflected the Navy's assessment of that value. SOSUS analysts developed over years of training and practice the ability to identify Soviet submarine classes from their acoustic signatures, the characteristic patterns of frequency and amplitude produced by a vessel's machinery, propellers, and hull resonances. Every submarine class has a distinctive acoustic profile produced by the specific combination of reactor type, propulsion machinery, propeller design, and hull construction used in that class. Within a class, individual submarines often have slightly different signatures, produced by variations in manufacturing tolerances, maintenance history, and equipment condition. SOSUS analysts learned to recognize these signatures the way an experienced sound engineer recognizes the acoustic character of a particular instrument. They could identify the class of a submarine from its broadband noise output, estimate its speed from its propeller blade rate, and in some cases identify a specific vessel from subtle features of its signature that distinguished it from others of the same class. This level of acoustic intelligence was possible because the SOFAR Channel delivered the submarine's acoustic output to the hydrophone arrays with enough fidelity to allow the detailed spectral analysis that these identifications required. The existence of SOSUS was officially declassified by the United States Navy in 1991, following the end of the Cold War and the dissolution of the Soviet Union. The declassification acknowledged the basic facts of the system: that a network of fixed underwater hydrophone arrays had been built and operated in the Atlantic and Pacific Oceans for the purpose of detecting and tracking Soviet submarines, without releasing details of array locations, specific capabilities, or the intelligence the system had produced. For scientists who had been studying underwater acoustics in the civilian sector, the declassification confirmed what many had suspected: that a large, sophisticated, and highly capable ocean acoustic monitoring infrastructure had been in operation for decades, and that the government's knowledge of underwater sound propagation was substantially more advanced than what had appeared in the public scientific literature. The declassification also opened a practical possibility that had not previously existed: the use of SOSUS infrastructure for civilian scientific research. Arrays that had been pointed at Soviet submarines could now be reoriented, at least partially, toward the ocean itself. Following declassification in 1991, the United States Navy made portions of the SOSUS network available for use by civilian scientists. Researchers at oceanographic institutions and universities were granted access to acoustic data from SOSUS arrays in the North Pacific and North Atlantic, subject to agreements governing data use and publication. The access was not complete. Some array locations and operational details remained classified, but it was sufficient to allow substantive scientific research. For oceanographers, the availability of SOSUS data was a significant development. The network provided basin-scale, continuous acoustic monitoring at SOFAR Channel depths, a capability that no civilian institution could have built independently. Questions about whale distributions, submarine earthquake activity, ocean temperature trends, and the ambient acoustic environment of the deep sea could now be addressed with a quality and geographic extent of data that had not previously been available to academic researchers. Within a few years of the initial data access agreements, SOSUS data had contributed to publications on blue whale acoustics, seismic monitoring, and ocean ambient noise, fields that had no overlap with the network's original military purpose. When civilian scientists first examined SOSUS acoustic data, many reported that the ocean's acoustic environment was significantly more complex and active than they had expected based on their prior research experience. Individual hydrophone deployments and small-scale experiments had provided useful data on local acoustic conditions, but they had not revealed the full character of the deep ocean's soundscape at basin scale. SOSUS data showed continuous activity across the frequency bands the channel propagated most efficiently. Low-frequency whale calls were present throughout the year in both ocean basins, with distributions and abundance patterns that required the full geographic coverage of the SOSUS network to resolve. Submarine earthquake signals appeared regularly in the data, often from sources too small and too remote to register clearly on land-based seismographs. And underlying the biological and geological signals was a persistent, broadband background noise that had been growing for decades. The accumulated acoustic output of commercial shipping, measurable now at continental scales because the SOFAR Channel was delivering it to every array in the network. The opening of SOSUS data to civilian researchers produced within a few years a catalogue of oceanic acoustic phenomena that had not previously been documented in the scientific literature. Blue whale call types unique to specific ocean populations were identified and described. Fin whale 20 Hz pulse patterns, previously known from limited deployments, were mapped across entire ocean basins. Acoustic signals from submarine volcanic eruptions along the mid-ocean ridges were detected and associated with specific eruption events. Ice-related sounds from the Southern Ocean and the Arctic were recorded at distances of thousands of kilometers from their sources. Several signals were detected that did not fit any known natural or anthropogenic acoustic category. Anomalous signals that required detailed investigation before their origins could be determined or, in some cases, left unresolved. The acoustic record that SOSUS had been accumulating for decades, originally compiled for the purpose of tracking submarines, turned out to contain a comprehensive and largely unstudied record of the ocean's natural acoustic activity. It was an archive that no one had built intentionally for scientific purposes, but that had scientific value across a range of disciplines. The central scientific finding that emerged from the first decade of civilian SOSUS research was a revision of the prevailing understanding of the deep ocean as an acoustically quiet environment. Prior to the availability of SOSUS data, the deep ocean's acoustic character had been studied through limited deployments of relatively few instruments. The picture that emerged from those studies was incomplete, accurate in detail but inadequate in scale. SOSUS data, covering entire ocean basins continuously over years, showed that the deep ocean was acoustically active at a level and complexity that the earlier, more limited studies had not captured. Biological signals were more numerous, more geographically widespread, and more temporally variable than the prior literature had indicated. Geological signals were more frequent and came from more diverse sources. The anthropogenic noise background was higher and more pervasive than any civilian study had established. The ocean had not been quiet. It had been unmonitored at sufficient scale to reveal its full acoustic character. SOSUS, built to listen for Soviet submarines, had inadvertently assembled the first comprehensive acoustic record of the deep ocean. And when scientists were finally allowed to examine it, they found an environment that had been speaking in detail for decades, unheard. The great baleen whales evolved their low-frequency vocalizations over a timescale measured in tens of millions of years. The SOFAR Channel has existed in the ocean for a comparable period, present in the deep ocean basins since the ocean's thermal and pressure structure reached something close to its current form. The alignment between the channel's most efficient propagation frequencies and the calling frequencies of the major baleen whale species, blue whales, fin whales, bowhead whales, is not coincidental. Evolutionary pressure consistently favored animals that could communicate over longer distances, and the SOFAR Channel offered a physical mechanism for long-distance acoustic communication to any animal calling at the right frequency and at sufficient depth. Over millions of years of selection, the great whales converged on vocalizations that are effectively optimized for SOFAR Channel propagation, low frequency, high source level, and produced at depths consistent with efficient coupling into the channel. This evolutionary convergence occurred without any awareness on the part of the animals of the physical mechanism involved. The channel did not need to be understood to be used. It only needed to reward, through improved communication range, the animals whose calls happened to propagate through it most efficiently. The baleen whales, the filter-feeding cetaceans that include blue whales, fin whales, sei whales, minke whales, and bowhead whales, produce some of the lowest frequency sounds in the animal kingdom. Their calls range from infrasonic frequencies below the threshold of human hearing up to the low audio range, typically between 10 and a few hundred hertz depending on the species. These low frequencies are not simply a byproduct of the animal's large size. They are functional adaptations for long-range communication in a medium, seawater, that transmits low-frequency sound with far less attenuation per unit distance than high-frequency sound. The physics of sound absorption in seawater strongly favors low frequencies for long-distance propagation. A 20 Hz signal attenuates at a rate orders of magnitude slower than a 20,000 Hz signal traveling the same path. Baleen whales exploit this property by calling at frequencies where the ocean's absorption is lowest and the SOFAR channel's propagation efficiency is highest. The result is a group of animals whose acoustic communication system is, in terms of raw physical range, the most capable of any known biological system. Blue whales produce calls whose fundamental frequencies regularly sit between 10 and 20 Hz, right at or below the lower threshold of human hearing. The standard lower limit of human auditory perception is approximately 20 Hz, though sensitivity at this frequency is poor in most individuals. Blue whale calls, which routinely center around 10 to 16 Hz, are below this threshold. They are infrasonic, pressure waves that pass through the body and surrounding environment without being consciously perceived by humans in proximity to them. Despite being inaudible to unaided human hearing, blue whale calls are among the most powerful biological sounds on Earth. Their source levels, the acoustic intensity at the point of production, have been measured at approximately 155 to 190 decibels relative to 1 micropascal at 1 meter, a range that places them among the loudest sounds produced by any living organism. At these source levels and at the frequencies involved, blue whale calls propagate through the SOFAR channel with exceptional efficiency, traveling far greater distances than the calls of any other known biological acoustic source. The SOFAR channel is most efficient as a waveguide in the frequency range of roughly 10 to 100 Hz. Below 10 Hz, acoustic wavelengths become very long relative to the channel's depth extent, and the channel's trapping efficiency decreases. Above a few hundred Hz, absorption losses in seawater increase significantly, limiting propagation range. The range of 10 to 100 Hz, the channel's acoustic sweet spot, corresponds closely to the calling frequencies of the major baleen whale species. Blue whales call at 10 to 40 Hz. Fin whales call at approximately 20 Hz. Sei whales and other baleen species call at frequencies within this range. This alignment between the channel's optimal propagation band and the biological calling frequencies of the animals that have used the ocean as a communication medium for millions of years is one of the most significant facts in the biology and physics of the ocean. It implies that the SOFAR channel has been a dominant selective pressure on the evolution of long-distance acoustic communication in large marine mammals, shaping over geological time the frequency structure of the calls of the ocean's largest animals. Scientists studying blue whale acoustics have estimated that, under favorable ocean conditions, blue whale calls may be detectable by other blue whales at ranges of up to 1,000 miles. This estimate is derived from calculations combining known blue whale source levels, measured SOFAR channel propagation losses at blue whale call frequencies, and estimates of blue whale hearing sensitivity at those frequencies. The range estimate is a maximum under optimal conditions, not a typical communication distance. Ocean conditions vary, background noise levels vary, and the exact geometries of source, channel, and receiver affect actual propagation performance. But even as an estimate of theoretical maximum range, 1,000 miles represents a communication capability without parallel in the biological world. No other animal is known to produce sounds with the potential to be detected by conspecifics at such distances. The SOFAR channel is the physical mechanism that makes this possible. By preserving acoustic energy over long distances through waveguide propagation, it extends the effective range of blue whale calls far beyond what would be achievable through free-field propagation in open water. Some researchers have proposed that in the pre-industrial ocean, before commercial shipping introduced significant low-frequency background noise into the SOFAR channel, blue whales may have been capable of acoustic communication across entire ocean basins, distances of several thousand miles. This proposal is based on calculations that combine blue whale source levels with estimates of pre-industrial ambient noise levels derived from acoustic models and limited historical measurements applied to SOFAR channel propagation models. The calculations suggest that the signal-to-noise ratio of a blue whale call at a range of several thousand miles may have been above the threshold for detection in a quieter ocean, even if it falls below that threshold in today's noisier environment. The proposal cannot be verified directly. Pre-industrial ocean acoustic conditions are not recoverable from direct measurement, but the supporting calculations are physically reasonable, and the evolutionary logic is consistent with the observed alignment between blue whale calling frequencies and the SOFAR channel's optimal propagation band. Whether blue whales actually communicated at transbasin ranges and whether such communication was behaviorally meaningful remains an open question. Fin whales produce a distinctive repetitive vocalization centered at approximately 20 Hz, a frequency that falls within the SOFAR channel's optimal propagation range and is produced with source levels sufficient for detection at ranges of hundreds to potentially thousands of kilometers. The 20 Hz call is produced by males and is believed to function as a long-range communication signal, though its exact behavioral role is not fully established. Following the opening of SOSUS data to civilian researchers in the 1990s, fin whale 20 Hz calls were detected and mapped across the North Atlantic and North Pacific at a spatial scale not previously achievable. The results showed that fin whale acoustic activity was distributed across entire ocean basins, with seasonal and geographic patterns that implied long-distance movement and possibly long-range acoustic interaction between individuals. The consistency of the 20 Hz call frequency across individuals and populations, unlike blue whale calls, which vary in frequency across populations and have been changing over time in some regions, has made fin whale acoustics a useful reference point for acoustic monitoring studies, and the call's alignment with SOFAR channel propagation characteristics continues to attract scientific attention. Sperm whales occupy a different acoustic niche than the baleen whales. They produce high-frequency clicks, impulsive sounds used for echolocation and social communication, rather than the low-frequency, long-duration vocalizations characteristic of baleen species. Sperm whale clicks do not propagate through the SOFAR channel in the long-range manner that blue and fin whale calls do, because high-frequency sounds are much more rapidly absorbed by seawater. However, sperm whales regularly dive to depths of 600 to 1,000 meters in pursuit of squid, depths that place them directly within the SOFAR channel zone. During these dives, their echolocation clicks and social coders are produced within the channel, even if the channel does not carry those sounds to the same long-range distances as lower-frequency vocalizations. The interaction between sperm whales and the SOFAR channel is less well characterized than the interactions of baleen whales with the channel, but the animal's regular presence at SOFAR depths during their foraging dives makes them a part of the channel's biological soundscape. Before the SOSUS network was opened to civilian researchers, knowledge of whale acoustic behavior at basin scales was severely limited. Individual hydrophone deployments and research vessel surveys had documented the calls of several species in limited geographic areas, but the spatial extent of these studies was a small fraction of the ocean environments the animals actually occupied. Population-level questions. How many blue whales are there in the North Pacific? Where do they concentrate in winter? How does their acoustic activity vary across years? Could not be addressed with the data that civilian researchers had access to. The fundamental problem was one of scale. Whales move over thousands of miles of ocean over the course of a year. Understanding their distribution and behavior requires monitoring over comparable spatial extents. SOSUS provided that scale for the first time, delivering continuous acoustic data from arrays distributed across entire ocean basins. The scientific literature on whale acoustics that emerged from the first decade of civilian SOSUS access was, in significant respects, a different discipline from what had existed before, operating at geographic scales, temporal extents, and detection sensitivities that prior studies had not achieved. In the late 1960s, biologist Roger Payne, working with engineer Scott McVeigh, analyzed underwater recordings made off Bermuda and identified in them a pattern of sound that had not previously been described for any animal. Long, complex, structured vocalizations produced by humpback whales organized into repeating sequences of distinct acoustic elements. Payne and McVeigh published their findings in 1971, describing what they called humpback whale songs, extended vocalizations that showed compositional structure analogous in some respects to the organization of birdsong. Payne also recognized that the acoustic properties of the ocean, its ability to transmit low-frequency sound over long distances, meant that humpback songs were not merely local events. A whale singing in the open Atlantic was producing a sound that the ocean could carry for hundreds or potentially thousands of miles. The recordings Payne made were released commercially in 1970 on an album that sold over 3 million copies and contributed to the public awareness of whale intelligence and the conservation movement that followed. The scientific recognition that whales produced structured, long-range acoustic signals was a significant development in the study of animal communication. Humpback whale songs occupy a higher frequency range than the infrasonic calls of blue and fin whales, with most acoustic energy between roughly 80 and 4000 Hz. This frequency range is above the SOFAR Channel's optimal propagation band, meaning that humpback songs do not benefit from the same degree of long-range waveguide propagation as the lower frequency calls of other baleen species. However, the ocean's acoustic properties still allow humpback songs to travel substantially farther than comparable sounds in air. Underwater absorption at the frequencies humpbacks use is low enough to permit propagation over tens to hundreds of kilometers, and in some ocean conditions significantly farther. The social and reproductive function of humpback songs, communicating mate quality and identity across the distances that separate whales in the open ocean, depends on this acoustic reach. Male humpbacks in competitive breeding areas can be heard by other males and potential females at distances that would be acoustically impossible in air, and the structure of their songs, which evolves gradually across a population over each breeding season, suggests ongoing acoustic communication at the population level. Bowhead whales, which inhabit Arctic and subarctic waters, produce songs of notable acoustic complexity and temporal variability. Researchers studying bowhead vocal behavior over multiple years have documented that the songs of individual whales change substantially from one year to the next. New acoustic elements appear, old ones disappear, and the overall compositional structure of songs shifts in ways that are inconsistent with genetic change. This pattern of rapid, non-genetic change in vocal behavior across a population is consistent with cultural transmission, the learning and modification of acoustic patterns through observation and imitation rather than inheritance. The geographic context is relevant. Bowhead whales live in the Arctic, where the SOFAR Channel is near the surface, and the acoustic environment is shaped by ice cover, seasonal variability, and the long-range propagation properties of cold polar water. The songs that individual bowheads produce in this environment can travel far beyond the immediate vicinity of the singing animal. Year-to-year changes in those songs, if they spread through the population via acoustic contact, represent a form of cultural evolution in a non-human species, a finding with significant implications for the study of animal cognition and social learning. The acoustic evidence accumulated from SOSUS data and subsequent research programs revised the scientific understanding of cetacean cognition and social organization in ways that had implications well beyond the study of whales. Animals that communicate over ranges of hundreds to thousands of miles, that produce vocalizations with compositional structure, that transmit acoustic patterns culturally across generations, and that maintain complex social relationships across oceanic distances are animals with cognitive capabilities that earlier scientific frameworks had not adequately accounted for. The behavioral and neurological complexity implied by long-range acoustic communication, the processing of signals that have traveled thousands of miles through a noisy medium, the production of structured vocalizations that vary individually and across populations, the apparent ability to update vocal repertoires in response to signals from distant conspecifics, placed cetacean intelligence in a different category than it had occupied in the mid-20th century scientific literature. The SOFAR Channel and the monitoring infrastructure built around it was central to producing this revision. Without basin-scale acoustic data, the full geographic extent of cetacean acoustic behavior would have remained unknown, and the cognitive and social complexity that behavior implies would have remained unrecognized. In 1989, analysts reviewing acoustic data from a SOSUS hydrophone array in the Pacific Ocean identified a vocalization that did not correspond to any known whale species in the Navy's acoustic library. The signal was biological in character, structured, repetitive, with the temporal and spectral properties of a large baleen whale call. Its frequency, however, was anomalous, 52 Hz, substantially higher than the characteristic call frequencies of any known baleen whale and lower than the typical vocalizations of smaller toothed cetaceans. Blue whales call between 10 and 40 Hz. Fin whales call at approximately 20 Hz. No known species produces regular calls centered at 52 Hz. The signal was documented and tracked as it appeared in subsequent years of data. By 1992, enough observations had accumulated to support a scientific publication describing the signal and noting the absence of any matching call from another individual in the acoustic record. The paper, published in the journal Deep Sea Research, attracted relatively little scientific attention at the time but would later become one of the most widely discussed facts in the popular literature on ocean acoustics. The 52 Hz whale was tracked across the North Pacific Ocean over multiple years using the SOFAR Channel and the SOSUS hydrophone array network. The signal appeared seasonally, consistent with migratory behavior, moving southward in late summer and fall and returning northward in spring. Its position at various times during each season was calculated from arrival time differences at multiple arrays using the same time difference of arrival method that Project SOFAR had demonstrated in 1944. The migration patterns were consistent with those of large baleen whales in terms of timing, directionality, and geographic extent. The animal behaved in its movement like a blue or fin whale. Only its calling frequency was anomalous. The SOFAR channel's long-range propagation properties were essential to tracking it. Without the channel's ability to carry the signal across hundreds of miles to multiple receiving arrays, the time difference calculations needed for position estimation would not have been possible. The 52 Hz whale is, in this respect, a product of SOFAR science, an animal whose existence and movements would have remained entirely unknown if not for the acoustic monitoring infrastructure that the SOFAR channel made possible. In every year during which the 52 Hz whale was tracked, and across the full acoustic database accumulated by SOSUS and subsequent civilian monitoring arrays, no other signal has been found at the same frequency. Blue whales produce their characteristic calls throughout the 52 Hz whale's range and migratory area. Fin whales produce their 20 Hz calls across the same ocean. Other baleen species contribute their respective vocalizations to the acoustic record. But at 52 Hz, the specific frequency of the anomalous animal, the record shows only one individual. If baleen whale acoustic communication depends on frequency matching between caller and receiver, if, in other words, a blue whale responds specifically to calls at blue whale frequencies and not to calls at other frequencies, then the 52 Hz whale exists in a state of acoustic isolation from every other large whale in the ocean. Its calls travel through the SOFAR channel with the same efficiency as any other low-frequency whale vocalization. They reach other whales. But no other whale in the recorded acoustic history of the North Pacific has called back at 52 Hz. The 52 Hz whale became known in popular culture as the loneliest creature on Earth after its story was covered in mainstream media in the early 2000s. The appeal of the narrative was clear. A single animal, calling continuously across an ocean, heard by no other whale in its own frequency range. The description captured public attention in a way that scientific acoustics rarely does. Songs were written about the animal. It became a widely circulated example in discussions of loneliness, isolation, and communication failure. Scientists were more cautious about the characterization. Whether the animal experienced anything comparable to loneliness in any behaviorally or neurologically meaningful sense is not determinable from acoustic data. And some researchers pointed out that the animal's behavior, its consistent migration, its continued calling over years, showed no signs of behavioral disruption that might be expected if acoustic isolation were causing distress. But the acoustic fact was not in dispute. In the frequency range of its calls, the 52 Hz whale had been heard by no conspecific in the recorded history of the Pacific Ocean. The species identity of the 52 Hz whale remains unestablished. No researcher has visually observed, photographed, or sampled the animal. What is known comes entirely from acoustic data. The migration pattern is consistent with a large baleen whale, most likely a blue whale or a species closely related to it. Several hypotheses have been proposed to explain the anomalous call frequency. The animal may be a hybrid between a blue whale and another baleen species. Blue-fin whale hybrids have been documented, and hybrids sometimes show intermediate acoustic characteristics. It may carry a physical abnormality of the vocal anatomy that shifts its call frequency above the normal range for its species. It may represent an extreme individual variation within a species whose normal call frequency range is broader than the typical values reported in the literature. None of these hypotheses has been confirmed. The 52 Hz whale remains acoustically active as of the most recent available records, its migration continuing, its frequency unchanged, its identity a matter of inference rather than direct observation. The story of the 52 Hz whale reached an audience far larger than the readership of the scientific journals in which it was originally described. It became a widely discussed example in popular writing on loneliness, communication, and the inner lives of animals. It appeared in news articles, essays, and eventually a documentary film. The acoustic facts at the center of the story: one animal, one frequency, decades of calling, no response at that frequency, translated easily into a narrative that was accessible and emotionally resonant to people with no background in ocean acoustics. What the story also communicated to some of the people who engaged with it was something about the SOFAR Channel itself. That the deep ocean was full of sound, that individual animals could be tracked over years and thousands of miles through acoustic monitoring, and that the physical properties of seawater created a communication medium of extraordinary range and complexity. The 52 Hz whale gave many people their first awareness that such a thing as the SOFAR Channel existed, that the ocean was not silent, and that something had been calling through its depths, unmatched, for longer than most people had known it was there. The SOFAR Channel carries every low-frequency acoustic event that occurs in the ocean with sufficient energy to propagate over long distances, biological, geological, and anthropogenic. When hydrophone arrays monitor this channel continuously over years and decades, they accumulate a record that includes not only well-characterized signal types but also signals that do not fit established categories. Some of these anomalous signals are eventually explained by improved understanding of known acoustic sources. Others are matched to specific geological or biological events identified through independent evidence. A small number have remained unexplained for years or decades, their geographic origin constrained but their source mechanism unresolved. These unidentified signals are a small fraction of the total acoustic record. The vast majority of what hydrophone arrays detect is noise from shipping, biological vocalizations, and known geophysical processes. But their existence reflects the incomplete state of scientific knowledge about all the acoustic sources operating in the deep ocean, and the SOFAR Channel's ability to deliver signals from remote, poorly monitored regions of the ocean floor to instruments positioned far away. On August 18, 1997, the National Oceanic and Atmospheric Administration's Autonomous Hydrophone Array Network in the Equatorial Pacific detected an ultra-low-frequency acoustic signal that was recorded simultaneously by multiple sensors separated by more than 5,000 kilometers. The signal lasted approximately 1 minute and showed a rising frequency pattern over its duration. NOAA analysts found no match for it in their reference library of known underwater acoustic signatures. The frequency profile was broadly consistent with a biological source, with the general character of a large animal vocalization, but the acoustic power of the signal was inconsistent with any known biological source. No animal on record produces enough acoustic energy to generate a signal detectable coherently by instruments 5,000 kilometers apart. NOAA released information about the signal publicly, giving it the informal name the bloop based on its acoustic profile as represented in audio playback. The release prompted widespread media coverage and considerable public speculation about its origin, most of which focused on the possibility of an unknown very large animal. The signal was not detected again at the same intensity. The fundamental problem with a biological explanation for the bloop was quantitative. Sound intensity decreases with distance as acoustic energy spreads over an expanding wavefront. Even accounting for the SOFAR Channel's efficiency in limiting geometric spreading losses, a signal detectable coherently across 5,000 kilometers must have originated with an extremely high source level, far beyond what any documented animal produces. Blue whales, the loudest known biological acoustic sources, produce calls at source levels of approximately 155 to 190 decibels relative to 1 micropascal at 1 meter. Calculations of the source level required to produce the bloop's observed detections across 5,000 kilometers indicated a level substantially higher than this range. The arithmetic did not support the biological hypothesis. Whatever produced the bloop, if it was a single-point source, was producing acoustic energy at a level that no known living organism approaches. This calculation did not rule out biological origin absolutely. It is possible, in principle, that a source with unusual acoustic directionality could produce a coherent long-range signal with lower total acoustic power than the isotropic source models assumed. But it made the biological hypothesis significantly less parsimonious than a non-biological explanation. In 2012, NOAA scientists published an analysis attributing the bloop to a large ice quake, The fracturing of glacial ice in the Antarctic region, where the Ross ice shelf and other glacial features periodically undergo large-scale mechanical failure. Ice quakes produce low-frequency acoustic signals that can be of very high power because the energy released in a large ice fracture event is substantial and is coupled directly into the ocean through the water in contact with the ice. The frequency profile of the bloop, including the rising pitch characteristic that gave it its name, is consistent with acoustic signatures observed from known ice fracture events. The geographic analysis of the bloop's origin pointed toward the Southern Ocean, consistent with an Antarctic glacial source. The 2012 analysis did not constitute a definitive identification of the specific ice feature responsible, but it provided a physically consistent and quantitatively adequate explanation for the signal's characteristics. The explanation was accepted by the oceanographic community as the most probable account of the bloop's origin, effectively closing the mystery that had been open since 1997. Since 1991, NOAA's Pacific Hydrophone Network has detected a recurring acoustic signal known as the upsweep, a series of narrow-band, upward-sweeping sounds that repeat over extended periods and are detectable across a broad area of the South Pacific. The upsweep is seasonal, with higher activity in spring and autumn than in summer and winter. Its geographic origin has been traced to a region of the South Pacific, though no specific source has been definitively identified. The leading hypothesis is that the upsweep is associated with submarine volcanic activity, possibly fluid or gas venting through the seafloor at a volcanic feature, generating sustained low-frequency acoustic emissions with a characteristic frequency sweep. The seasonal variation in the signal's intensity is not fully explained by this hypothesis, as volcanic activity does not typically follow a seasonal pattern. The upsweep has been detected in every year since its discovery, making it one of the most persistent anomalous signals in the hydrophone record. Its source remains the subject of ongoing investigation. In the spring of 1997, NOAA's Pacific Hydrophone Array detected an acoustic signal characterized by a sustained decrease in frequency over approximately 7 minutes, a pattern that gave it the informal name, the slowdown. The signal was detected across a broad area of the South Pacific, and its geographic origin was estimated to be in the vicinity of Antarctica. Like the bloop, which was detected in the same year, the slowdown has been attributed by researchers to ice or seismic activity in Antarctic or subantarctic waters. A decreasing frequency profile is consistent with some models of acoustic emission from ice fracture events, in which the acoustic character of the signal changes as the fracture propagates through the ice mass and the physical properties of the radiating structure evolve. The slowdown was not detected again at the same intensity after its initial recording, which is consistent with a single large ice fracture event rather than an ongoing source. It is classified in the NOAA Anomalous Signals database as an event of probable glaciological or seismic origin, with the specific source mechanism unconfirmed. On March 1, 1999, NOAA's Equatorial Pacific Hydrophone Network detected a 15-second acoustic signal that analysts described informally as resembling a voice saying the name Julia. The informal name stuck. The signal was detected across a broad area of the South Pacific, and its geographic origin was estimated to be near Antarctica. Analysis of the signal's frequency content and duration suggested a glaciological origin, specifically the sound of a large iceberg running aground on the Antarctic seafloor. When a large tabular iceberg drifting under the influence of ocean currents contacts the seafloor in shallow water, the mechanical interaction generates low-frequency acoustic energy that can enter the SOFAR Channel and travel thousands of kilometers. The 15-second duration and the specific frequency character of the Julia signal are consistent with this mechanism. The iceberg hypothesis is the standard explanation given for Julia in NOAA's documentation of anomalous hydrophone detections, though the specific iceberg responsible was not identified. Also in 1997, NOAA's Pacific Hydrophone Network detected a signal characterized by a nearly continuous, rhythmically regular acoustic output, a pattern that analysts named train for its steady, repetitive character. The signal's geographic origin was traced to the general region of seismically active seafloor in the South Pacific. The leading hypothesis for train is submarine volcanic activity, in which sustained geological processes generate a relatively steady acoustic output with the rhythmic quality observed in the recorded signal. Submarine volcanoes and hydrothermal vent systems can produce sounds that, after propagating thousands of kilometers through the SOFAR Channel, arrive at receiving arrays with an altered character compared to their output at the source. The filtering and propagation effects of long-range ocean acoustics can transform an irregular geological noise into a signal that sounds, to a human observer, almost periodic. Train's source mechanism has not been definitively identified, and it remains in the category of signals whose geographic origin has been estimated, but whose generating process has not been confirmed through direct observation of the source area. The bloop, the upsweep, the slowdown, Julia and Train share a common characteristic. None of them would have been detectable by any instrument without the SOFAR Channel. The events that produced these sounds, ice fracture, submarine volcanism, iceberg grounding, occurred in remote locations, thousands of kilometers from the nearest hydrophone array. The acoustic energy from each event spread outward from its source. Without the SOFAR Channel's waveguide properties to preserve that energy over long distances, the signals would have attenuated to inaudibility within a fraction of the distance between their sources and the receiving arrays. The SOFAR Channel did not create these sounds. It carried them across ocean basins at 1,500 meters per second, losing energy only to the gradual absorption of seawater and the slow geometric spreading of the wavefront. By the time the signals reached the arrays, they had traveled thousands of kilometers, but they retained enough coherence and amplitude to trigger detection algorithms and appear in the acoustic record. Every unexplained sound in the SOFAR monitoring database is, in this sense, a fact about the channel as much as a fact about its source. Evidence that the ocean's acoustic corridor can deliver information from the most remote environments on Earth to the instruments that have been positioned to receive it. Ocean acoustic tomography is a technique for measuring the temperature of large volumes of ocean water using the travel time of acoustic pulses transmitted through the SOFAR Channel. The underlying principle is that sound travels faster through warmer water than through cooler water, so the time it takes a pulse to travel a known distance through the channel encodes information about the average temperature of the water along the propagation path. An acoustic tomography system consists of a source that transmits precisely coded low-frequency pulses into the SOFAR Channel and one or more receivers at known distances that record the arrival times of those pulses. By comparing observed travel times to predicted travel times based on a reference sound speed profile, researchers can calculate deviations from the reference temperature, regions where the water is warmer or cooler than the baseline, averaged along the acoustic path. By using multiple intersecting acoustic paths, the technique can produce a three-dimensional temperature map of a large ocean volume. The method was proposed by Walter Munk and Carl Wunsch in a 1979 paper that has been called one of the most influential in the history of physical oceanography. The accuracy with which acoustic tomography can infer ocean temperature depends directly on the precision with which pulse travel times are measured. Sound traveling through the SOFAR Channel at 1,500 meters per second covers 1,500 meters per second. A timing error of 1 millisecond corresponds to a range error of 1.5 meters. For a path of 1,000 kilometers, the total travel time is approximately 667 seconds. Temperature changes along the path alter this travel time by amounts on the order of 1 to several seconds for temperature anomalies of practical interest in climate research. Modern acoustic tomography systems achieve timing precisions of a few milliseconds over 1,000-kilometer paths, enabled by GPS, synchronized clocks, and specially designed pulse codes that allow precise arrival time determination even against background ocean noise. The technical challenge is substantial. Synchronizing clocks separated by 1,000 kilometers of ocean to millisecond accuracy, deploying acoustic sources capable of producing low-frequency pulses at the necessary source level, and maintaining receivers capable of detecting and recording those pulses over months to years of autonomous operation. Several large-scale tomography experiments have been conducted since the 1980s, demonstrating the feasibility of the method at ocean basin scales. The sensitivity of ocean acoustic tomography to temperature variations is a consequence of the physics of sound propagation in seawater. Sound speed in the ocean increases by approximately 4 to 5 meters per second for each degree Celsius increase in temperature. Over an acoustic path of 1,000 kilometers, a temperature increase of 1 degree Celsius averaged along the path would reduce travel time by approximately 3 seconds, a change that modern timing systems can detect reliably. This means that acoustic tomography can resolve basin-scale temperature changes of a fraction of a degree Celsius, far smaller than the temperature anomalies associated with large-scale ocean circulation events and climate variability. Conventional temperature sensors measure conditions at a single point. An acoustic tomography system measures the average temperature along the entire path between source and receiver, providing a spatial average that is more representative of large-scale ocean heat content than any practical network of point measurements. Multiple acoustic paths crossing the same ocean volume provide constraints on the three-dimensional temperature structure, allowing researchers to distinguish depth-integrated warming from warming confined to specific depth ranges. Ocean acoustic tomography has been applied to the measurement of ocean warming trends at basin scales, contributing data that is directly relevant to climate monitoring. The ocean has absorbed a substantial fraction of the excess heat added to the Earth system by anthropogenic greenhouse gas emissions since the mid-20th century, and tracking the magnitude and distribution of this heat uptake is an important component of climate assessment. Acoustic tomography provides a method for measuring basin-scale ocean heat content changes with high temporal resolution and without the logistical challenges of deploying large numbers of individual temperature sensors. Experiments conducted in the North Pacific and other ocean regions have documented changes in SOFAR Channel acoustic travel times consistent with basin-scale warming trends documented by other methods. The tomographic data provides an independent check on Argo float and ship-based temperature measurements, and its spatial averaging properties make it particularly useful for detecting large-scale trends against the background of smaller-scale natural variability. One of the limitations of conventional ocean temperature monitoring, ship-based measurements, moored instruments, profiling floats, is that it provides point or near-point observations of a system that varies continuously in 3 dimensions. Statistical methods can be used to infer large-scale temperature fields from networks of point observations, but the accuracy of those inferences decreases as the spatial density of observations decreases. In the deep ocean, away from shipping routes and standard hydrographic sections, the spatial density of conventional temperature observations is low. Acoustic tomography addresses this limitation by providing path-integrated temperature measurements that inherently sample the entire volume of water between source and receiver. A single acoustic path crossing 3,000 kilometers of deep Pacific Ocean averages the temperature of all the water in the SOFAR Channel along that path, weighting the average by the fraction of travel time spent in each depth range. Multiple paths allow the deconvolution of this average into depth-dependent temperature profiles. The result is temperature information for ocean regions where direct measurements are sparse, obtained at temporal resolution limited only by the repetition rate of acoustic pulse transmissions, potentially as frequent as once per hour. Underwater earthquakes transmit acoustic energy into the water column above the rupture zone, generating signals that enter the SOFAR Channel and travel to hydrophone arrays at distances of hundreds to thousands of kilometers. These hydroacoustic signals, called T-phases in seismological terminology, travel through the SOFAR Channel at the speed of sound in water, arriving at distant receivers much faster than seismic waves traveling through the solid Earth over comparable distances. For earthquakes occurring on the mid-ocean ridges and in other oceanic settings far from land, T-phases recorded by hydrophone arrays may be the clearest available signal, because the seismic waves from these events have attenuated significantly by the time they reach land-based seismographs. The global hydrophone network monitoring the SOFAR Channel has contributed substantially to earthquake catalogues for oceanic regions, adding events at magnitudes below those detectable by the land-based seismic network. This improved catalogue has implications for understanding the seismicity of submarine tectonic structures, assessing the hazard from submarine landslides and tsunamis, and characterizing the statistical properties of earthquake occurrence at mid-ocean spreading centers. The Comprehensive Nuclear Test Ban Treaty Organization operates a global monitoring system designed to detect nuclear explosions wherever they occur. The hydroacoustic component of this system consists of hydrophone stations positioned in the SOFAR Channel at 6 primary locations around the world's oceans. These stations are designed to detect the low-frequency acoustic signals that underwater or near-coastal nuclear explosions would produce, signals that, at the relevant frequencies, propagate through the SOFAR Channel over thousands of kilometers with enough amplitude to be detected by sensitive instruments. The detection threshold of the CTBTO hydroacoustic network, the minimum explosion yield that can be reliably detected, is below the threshold of any weapon with practical military utility. A nuclear test conducted underwater anywhere in the ocean would produce a T-phase signal in the SOFAR channel that would be recorded by multiple CTBTO stations within hours. The network has also detected a range of non-nuclear acoustic events during its operational history, including underwater earthquakes, iceberg groundings, and underwater volcanic eruptions, demonstrating the breadth of the monitoring capability that the SOFAR channel provides. The land-based global seismic network can reliably detect earthquakes of magnitude 3.5 or greater almost anywhere on Earth. In oceanic regions, particularly on the mid-ocean ridges far from the nearest land station, the detection threshold for surface seismic networks is typically higher, magnitude 4 or greater for reliable detection, and often higher for small events in remote ocean regions where station coverage is sparse. Hydrophone arrays listening in the SOFAR channel extend the detection capability into the magnitude 2 to 3 range for many oceanic seismic zones, because T-phase energy propagates through the water column with less attenuation than seismic waves traveling through the oceanic crust to distant land stations. The earthquake catalogues produced by combining land-based seismic data with hydroacoustic T-phase data are substantially more complete for oceanic regions than those based on seismic data alone. These more complete catalogues have revised scientific understanding of the frequency and distribution of small seismic events on mid-ocean ridges and transform faults, and have provided context for interpreting the occasional large submarine earthquakes that generate tsunamis and other significant hazards. Every significant movement of the seafloor, fault rupture, volcanic eruption, mass wasting, caldera collapse, transfers acoustic energy into the water column and, from there, into the SOFAR channel. For researchers studying the geology and tectonics of the deep ocean floor, this means that the hydrophone network provides a near real-time record of acoustic events on the seafloor, often at distances and spatial scales that preclude direct observation by research vessels or remotely operated vehicles. A submarine volcanic eruption on the mid-ocean ridge can be detected by SOFAR hydrophone arrays within minutes of its onset. Its duration, spatial extent, and approximate intensity can be inferred from the acoustic record. A submarine landslide, a geological event that can generate tsunamis and significantly modify seafloor topography, produces a distinctive acoustic signature that can be distinguished from other types of seismic events by its frequency content and temporal structure. The SOFAR channel delivers this geological information across ocean basins to receiving stations, providing a continuous monitoring capability for seafloor processes that would otherwise be accessible only through direct observation at the site. Large tabular icebergs carving from the Antarctic ice sheet produce acoustic signals as they drift northward through the Southern Ocean, grinding against other ice, scraping the seafloor in shallow waters, and carving smaller fragments from their edges. These sounds, at low frequencies, enter the SOFAR channel and propagate to hydrophone arrays distributed around the Southern Ocean and beyond. Researchers have used SOFAR acoustic data to track the positions of specific large icebergs over months and years, correlating acoustic signals with radar satellite imagery to establish the relationship between a detected acoustic source and the physical iceberg producing it. Acoustic iceberg tracking provides position information for icebergs that are too remote for regular aerial or ship-based surveillance, and with a time resolution that satellite passes alone cannot always achieve. The tracking data is used in both scientific studies of Southern Ocean circulation. Icebergs affect ocean salinity and temperature as they melt, and in operational applications such as hazard assessment for shipping and research vessel routing in Antarctic waters. Acoustic travel times measured through the SOFAR channel carry information not only about average ocean temperature but also about the mesoscale variability of the ocean's circulation. Large rotating eddies, coherent structures 100 to 300 kilometers in diameter that form and dissipate on timescales of weeks to months, contain water that is warmer or cooler than the surrounding ocean, depending on whether the eddy is rotating cyclonically or anticyclonically. When an acoustic pulse travels through a warm core eddy, it moves through faster than average water and arrives slightly earlier than predicted by a background temperature model. When it travels through a cold core eddy, it arrives slightly later. By analyzing systematic patterns in travel time residuals from multiple acoustic paths crossing the same ocean region, researchers can track the positions and intensities of mesoscale eddies over time without the intensive ship surveys that would otherwise be required. This application of SOFAR acoustics to ocean circulation monitoring bridges the gap between the large-scale temperature monitoring provided by basin-scale tomography and the point-by-point measurements of the Argo float array. The combined application of the SOFAR Channel to submarine detection, earthquake monitoring, climate measurement, iceberg tracking, and whale observation represents an acoustic monitoring capability without parallel in any other Earth system. No other single physical feature of the ocean provides simultaneous access to biological activity, geological events, and large-scale physical oceanographic variability at basin scales, and with the temporal resolution that the SOFAR channel delivers to hydrophone arrays. The channel does not distinguish between the signals it carries. A blue whale call, an earthquake T-phase, a tomographic research pulse, and the low-frequency noise of a container ship all travel through the same corridor by the same physical mechanism. The hydrophone arrays that monitor the channel receive all of these signals simultaneously, and the scientific and operational value they extract from that continuous acoustic stream spans a range of disciplines from seismology to climate science to marine biology. The ocean, through the SOFAR channel, reports on its own state with a completeness and geographic coverage that no deployable sensor network has yet matched. Since the mid-20th century, the ambient noise level in the world's oceans has increased substantially in the frequency bands most relevant to the SOFAR channel. The increase is documented in long-term records from hydrophone networks and in analyses comparing current ambient noise levels to historical baselines estimated from physical models and limited early measurements. The primary driver of this increase is commercial shipping. The growth of global maritime trade over the past 70 years has produced a corresponding growth in the number, size, and acoustic output of vessels operating in every major ocean. Each ship produces a continuous low-frequency acoustic signature from its propulsion machinery and hull vibration. The cumulative contribution of tens of thousands of vessels operating simultaneously has raised the background noise level in the SOFAR channel's most efficient propagation frequencies by a measurable amount across large areas of the ocean. This noise increase is not uniform. It is highest along major shipping lanes and lowest in remote ocean regions far from commercial routes, but it is present throughout the ocean basins that global shipping traverses. A modern large container ship generates low-frequency acoustic noise continuously during operation, with most of its acoustic output concentrated between approximately 10 and 100 Hz, the same frequency range in which the SOFAR channel propagates sound most efficiently. The primary noise sources are propeller cavitation, which produces broadband noise as water vapor bubbles form and collapse on the propeller blade surfaces, and machinery noise from the engines and transmission systems, which produces tonal components at the shaft rotation frequency and its harmonics. The source level of a large container ship at these frequencies is approximately 175 to 195 decibels relative to 1 micropascal at 1 meter, comparable to or exceeding the source levels of blue whale calls. This noise is produced without interruption for the duration of each voyage. A vessel crossing the Atlantic takes approximately 7 days. For those 7 days, its acoustic signature propagates into the surrounding ocean and, at the relevant depths and frequencies, couples into the SOFAR channel and travels outward in all directions. At any given moment, the North Atlantic SOFAR channel contains the overlapping acoustic signatures of hundreds of ships simultaneously in transit. The global commercial shipping fleet includes more than 50,000 vessels of significant size in active operation at any given time. Each produces a continuous low-frequency acoustic signature. Their combined contribution to ocean ambient noise in the SOFAR channel frequency range has been estimated from acoustic models and direct measurements. Studies examining long-term trends in ocean ambient noise using historical hydrophone data have documented increases of approximately 10 to 20 decibels in low-frequency ambient noise levels in many ocean regions since the 1960s. The decibel scale for acoustic power is logarithmic. An increase of 10 decibels represents a 10-fold increase in acoustic power, and an increase of 20 decibels represents a 100-fold increase. These measurements therefore indicate that low-frequency ambient noise levels in heavily trafficked ocean regions have increased by a factor of 10 to 100 times compared to the pre-shipping baseline. This increase is distributed unevenly across the ocean. Shipping lanes carry the highest noise levels, but the SOFAR channel's long-range propagation properties mean that noise from heavily trafficked routes is audible across entire ocean basins. The increase in ocean ambient noise from commercial shipping is not inferred from models alone. It is documented in measured acoustic data extending back to the 1960s, when the SOSUS network and early civilian hydrophone deployments began accumulating baseline records of ocean ambient noise. Analyses of this historical acoustic data, conducted by multiple research groups using independent methodologies, have consistently found upward trends in low-frequency ambient noise levels that correlate with the growth of global shipping traffic over the same period. The SOSUS network, designed to detect submarines in the SOFAR Channel, was also continuously recording the ambient noise background against which it was trying to detect those submarines, and that ambient noise record provides a multi-decade baseline for tracking changes in the ocean's acoustic environment. Subsequent analyses of SOSUS ambient noise data have quantified the noise increase attributable to shipping with a precision that would not have been achievable from shorter records or less spatially comprehensive datasets. The increase in low-frequency ambient noise in the SOFAR Channel has direct consequences for baleen whales that use the channel for long-range communication. The maximum distance over which a whale call can be detected above background noise, the effective communication range, is determined by the ratio of signal level to ambient noise level at the receiver location. As ambient noise increases, this ratio decreases and the effective communication range shrinks. A blue whale call that could be detected by a conspecific at a range of 500 kilometers in a quieter ocean might be detectable at only 50 kilometers in an ocean with a 20 decibel higher noise background, a 10-fold reduction in linear range, corresponding to a 100-fold reduction in the ocean area over which the call is audible. The reduction in effective communication range affects the ability of whales to locate mates, maintain contact with other members of their social group, and coordinate movements over the oceanic distances that characterize baleen whale behavior. Because the noise increase and the communication frequency range of baleen whales overlap substantially, the impact is not merely theoretical. Researchers have estimated that the effective communication range of blue whales may have been reduced by as much as 90% compared to pre-industrial ocean conditions, as a result of the increase in low-frequency ambient noise from commercial shipping. This estimate is derived by combining measured increases in ambient noise levels with blue whale source levels, SOFAR channel propagation models, and estimates of blue whale hearing sensitivity at call frequencies. The 90% reduction in range corresponds to the difference between an estimated pre-industrial communication range of roughly 1,000 kilometers and a current effective range of roughly 100 kilometers in heavily trafficked ocean regions. In quieter ocean areas, away from major shipping lanes, in remote ocean basins, the reduction is smaller because ambient noise levels there remain lower than along primary shipping routes. The estimate carries uncertainty from several sources, including the difficulty of establishing a reliable pre-industrial noise baseline and the uncertainty in blue whale hearing sensitivity measurements. But across the range of reasonable assumptions, the direction of the effect is consistent. The SOFAR Channel's utility for baleen whale communication has been substantially degraded by anthropogenic noise. Commercial shipping noise is not the only form of human acoustic activity affecting marine mammals through the SOFAR Channel. Military sonar, particularly high-powered mid-frequency active sonar used by naval vessels for submarine detection, produces intense acoustic signals that, while at higher frequencies than the SOFAR Channel's optimal propagation range, can reach high amplitudes at relatively close ranges and may affect marine mammals at distances of tens to hundreds of kilometers. Multiple episodes of mass strandings of beaked whales have been documented in temporal and geographic proximity to naval exercises using active sonar. Beaked whales, which dive to SOFAR Channel depths during foraging, appear to be particularly sensitive to mid-frequency sonar exposure. Proposed mechanisms for sonar-related strandings include acoustic trauma, behavioral responses that lead to dangerous ascent rates, and gas bubble formation analogous to decompression sickness. Regulatory agencies in several countries have imposed restrictions on sonar use in areas with high concentrations of beaked whales based on the documented association between sonar exercises and stranding events. The SOFAR Channel of the contemporary ocean is acoustically different from the channel that existed before commercial shipping became a global industry. The physical structure of the channel is unchanged. The temperature and pressure gradients that define it have not been altered by human activity in any measurable way, and its propagation properties remain those described by the physics of underwater acoustics. What has changed is the content of what travels through it. The channel carries not only the biological and geological signals it has carried for millions of years, whale calls, earthquake T-phases, iceberg sounds, volcanic emissions, but also the continuous broadband low-frequency noise output of global commercial shipping distributed throughout the ocean basins and present at every hour of every day. This noise does not degrade the channel's physical properties. It shares the channel with every other acoustic source the channel carries. But its presence raises the noise floor against which all other signals must be detected, reducing the effective range of biological signals, obscuring the finer features of geological acoustic signatures, and creating an acoustic background that did not exist when the channel's biological users evolved their communication systems within it. Despite 8 decades of research and the accumulation of acoustic data from global hydrophone networks, the SOFAR channel continues to deliver signals that have not been definitively explained. Some have been attributed to probable source categories, glaciological, volcanic, biological, without specific source identification. Others remain in an open category, waiting for additional data or improved analysis methods that might resolve their origin. This residue of unexplained signals is not large relative to the total volume of acoustic data in the hydrophone record, but it is persistent. The deep ocean covers more than 70% of the Earth's surface, and direct observation of the seafloor is limited to a small fraction of that area. The SOFAR channel receives acoustic signals from regions that have never been directly surveyed. Remote segments of mid-ocean ridges, deep ocean trenches, isolated submarine volcanic features, and the acoustic record is sometimes the only observation available for these environments. When a signal from such a region does not match any reference in the current library of known acoustic sources, it either reflects a gap in that library or the presence of a source that science has not yet characterized. Both possibilities remain open for some signals currently in the unresolved category. The ocean covers approximately 71% of the Earth's surface and has a mean depth of roughly 3,700 meters. Its total volume is approximately 1.335 billion cubic kilometers. The acoustic environment of this ocean, the SOFAR channel, the biological and geological sources that supply it with signals, the anthropogenic noise that has been added to it over the past century, constitutes one of the least studied acoustic environments on the planet relative to its size and significance. Systematic acoustic monitoring at basin scales has been possible for only about 3 decades since the opening of SOSUS data to civilian researchers in the early 1990s. The scientific literature on deep ocean acoustics, while substantial, reflects only a beginning. The processes that generate sound in the deep ocean span a range from individual whale vocalizations to basin-scale circulation changes to major tectonic events, and the interactions among these processes and with the acoustic monitoring systems designed to detect them are incompletely understood. The SOFAR channel provides the medium through which this acoustic environment can be studied, but the scale of what remains to be learned about it is proportional to the scale of the ocean itself. Within a single ocean basin, the SOFAR channel connects distant points into a continuous acoustic space. A low-frequency acoustic signal produced in the waters off the Russian Pacific coast can, under appropriate conditions of source depth and frequency, propagate through the North Pacific SOFAR channel and be detected by instruments positioned off the coast of California, a distance of more than 8,000 kilometers. This is not a theoretical extrapolation. Acoustic transmissions of this scale have been conducted as part of ocean acoustic tomography experiments and confirmed by direct detection at the receiving end. The travel time for such a signal, at typical SOFAR channel propagation speeds of approximately 1,480 meters per second in the North Pacific, is roughly 1.5 hours. During that hour and a half, the signal has passed through millions of cubic kilometers of ocean, interacting with everything in its path, warm eddies, cold fronts, mesoscale circulation features, and has arrived at its destination with the thermal history of its journey encoded in its travel time. The California receiver does not see the Russian coast, but through the SOFAR channel it hears a precise representation of everything the intervening ocean did to the speed of sound during the preceding 90 minutes. The SOFAR channel functions, in a practical sense, as a temporary acoustic memory for the ocean. At any given moment, the channel contains signals in transit from a range of sources: earthquakes that occurred hours ago, whale calls produced thousands of kilometers away, iceberg sounds still traveling northward from Antarctic waters. These signals are not stored in the channel in any permanent sense. They are physical pressure waves moving through the water at 1,500 meters per second, and they will dissipate when they encounter the boundaries of the ocean basin or when their energy has been absorbed by the water itself. But for the duration of their transit, hours in most cases, they are present in the channel as a physical record of the events that produced them. A hydrophone positioned anywhere in the channel is, at any moment, receiving a sample of everything acoustically significant that has happened in the ocean over the preceding hours within propagation range. This temporal depth, the fact that the channel's current acoustic content reflects events distributed over hours of prior time, is one of the properties that makes it useful for monitoring purposes. The SOFAR Channel is geologically ancient. The physical conditions that create it, a thermally stratified ocean with a cold, deep layer underlying a warmer surface layer combined with the pressure gradient that increases with depth, have existed in the world's ocean basins for tens of millions of years since the ocean reached something close to its present thermal structure. The channel predates the existence of the great baleen whales by a significant margin. It was present in the ocean when the ancestors of today's cetaceans were transitioning from terrestrial to marine existence, roughly 50 million years ago. It has been available as a propagation medium throughout the entire evolutionary history of the group. The alignment between baleen whale calling frequencies and the SOFAR channel's optimal propagation range, noted earlier as a probable product of evolutionary selection, reflects this long coexistence. Over the course of cetacean evolution, the channel has been a consistent physical feature of the acoustic environment that shaped selection pressures on cetacean vocalization. The animals that exist today, calling at frequencies optimized for SOFAR propagation, are the product of 50 million years of evolutionary pressure applied by a physical feature of the ocean that preceded their existence and will persist long after it. The SOFAR channel carries, at any given moment, a simultaneous record of acoustic events spanning the full range of sources operating in the deep ocean. Low-frequency calls from blue whales migrating through the North Pacific, the 20 Hz pulses of fin whales in the North Atlantic, earthquake T-phases from seismic events on mid-ocean ridges detected within minutes of the rupture, the continuous broadband noise of container ships on transoceanic routes, the grinding and carving sounds of icebergs drifting north from Antarctica, acoustic tomography pulses from research transmitters in the Indian Ocean. Each of these signals occupies the same physical channel, propagating through the same water by the same mechanism, delivering itself to the same hydrophone arrays that monitor the channel's content. The channel does not prioritize or filter. It carries them all with equal efficiency. The arrays that receive this signal mix, and the scientists and operators who analyze it, apply the differentiation that the channel itself does not make, using frequency, timing, source direction, and signal structure to separate whale from ship, from earthquake, from iceberg. The channel's indifference to source type is, from the monitoring perspective, a feature rather than a limitation. One of the most durable misconceptions about the deep ocean is that it is quiet. The popular image of the ocean's depths as a silent, dark environment is not accurate. The deep ocean, particularly in the frequency band of the SOFAR channel, is one of the more acoustically active environments on Earth. It contains the calls of multiple whale species, the acoustic output of geological processes including seismicity and volcanism, the noise of shipping and other human activities, and the physical acoustic noise of the ocean's own circulation, the movement of water masses, the formation and dissolution of eddies, the interaction of the ocean with weather at the surface. All of these sources contribute to the ambient acoustic environment of the SOFAR channel continuously and simultaneously. The channel carries their combined output across ocean basins, delivering a continuous sample of this complex acoustic environment to every hydrophone array positioned within it. The misconception of oceanic silence likely persists because the frequencies at which the deep ocean is most acoustically active are below the threshold of human hearing, and because the propagation medium, water, is inaccessible to direct human acoustic experience without specialized instruments. But the instruments are clear on the matter. The SOFAR channel is a consequence of physics, of temperature and pressure, and the way they affect the speed of sound in seawater. It requires no special explanation beyond the application of well-established physical principles to the conditions that exist in the deep ocean. But the scope of what it has enabled and what it continues to carry gives it a significance that extends well beyond its physical description. It is the medium through which blue whales may have communicated across ocean basins for millions of years. It is the infrastructure on which the Cold War's most extensive surveillance network was built. It is the pathway through which scientists now measure the temperature of entire ocean basins with millisecond timing and track the movements of icebergs thousands of kilometers from their points of origin. It carries earthquake signals from the remote mid-ocean ridges to instruments that add those events to the global seismic catalogue. It carries shipping noise from the world's trade routes to the ears of whales trying to communicate across distances that the noise is systematically reducing. At this moment, the SOFAR Channel contains all of these signals simultaneously, moving through cold, dark water at 1,500 meters per second, arriving at instruments positioned to receive them, carrying the acoustic record of everything the ocean knows. The SOFAR Channel runs through every ocean on Earth right now, carrying whale calls, earthquake signals, and the noise of 10,000 ships all at once, all unseen. It has been there since before the first whale ever called into it. It will be there long after the last one does. The ocean is not quiet. It has never been quiet. Below the surface, in the cold and the dark, something is always moving through the channel, and if you had the instruments to hear it, you would never mistake the deep sea for silence again. Sleep well.